Okay, we are live. Okay, so hello everyone. It's a pleasure to introduce in the Parallel Live seminar Professor Simone Campanoni. He is a tenure track assistant professor at the computer science department at Northwestern University, where he runs the ARCANA research group. And his main research is in compilers with special interest in the relationship with computer architecture, runtime system, operating systems, and programming language. And today he's going to talk a little bit about the source of his group, the special source that his group has developed over some time. So feel free to ask any question over Zoom or over YouTube as well. You're going to redirect Professor Simone. So hope you enjoy this talk, and thanks so much for being here today.
Thank you for the great introduction. By the way, your pronunciation was perfect.
Oh, thanks.
Perfectly.
Thanks for having me here.
So, hello everyone. Thank you for being here at my talk, and feel free to ask me questions at any point in time. Every question is good. Like I like to be involved both at the conceptual level of research as well as development. I really love programming. So if you have questions at the code level, at the implementation level, feel free to ask as well. Any question is fine. So what I'm going to talk about in the next hour or so is a new way of thinking, a new way of implementing advanced code transformations. So we need innovation in advanced code transformations. We need it yesterday, today, and even more in the future. The reason is because the hardware is getting more and more complex, more and more heterogeneous, and rewriting the software for different type of architectures is just not sustainable in terms of maintainability and therefore costs. So advanced code transformations could be an interesting solution to alleviate the cost of mapping software into complex hardware and unleashing the full potential of the hardware. So we need a lot of innovation, which means we need to test ideas very quickly. And in my group, together with my collaborators, we built our secret sauce, which is a new way of writing these advanced code transformations in few lines of code in a little bit of time. We leveraged that in the last 7 years, and we published papers with it. And we found it so useful that I decided to open source the entire infrastructure. I'm giving tutorials on YouTube right now on how to use it and giving talks. And the hope is other people, other groups will find useful what we build and this new way of thinking about transformations. In general, my group is interested to understand how abstractions within compilers could and should evolve to better sustain the needs of modern workloads and modern hardware. We are also interested in understanding how abstractions around compilers, let's say with the hardware or with the operating system, should evolve to unleash the full potential of the innovation we bring in compilers. So we think about abstractions a lot. Now, to fully understand, for me to better explain the uniqueness of this new way of implementing transformations, I need to contextualize it in the whole history of compilers. You know, it might seem a lot, but like I'm going to do this relatively quickly. So first of all, I'm really happy to be here and to talk to your university because the entire field of compilers was started here at ETA. I don't know if you know, but like in 1951, one of the first PhD theses that was given to what we call today computer science was given to Corrado Bohm, which wrote in his PhD the fundamental algorithms that we leverage to do compilers or compilation pipelines. It was only on paper back then, but the year after, with Grace Hopper coined the word compilers. And she introduced the first compiler called A0. Now, with our modern understanding what compiler is, what she built back then is what we would call today a loader and a linker. And it was with the AutoCode project that we have the first compiler in the sense that we mean today. And the first compiler was the AutoCode that was for the architecture Manchester Mark I, which was developed together with Alan Turing. Now, at this point, we had the first phase of compilers. I call it the first phase because compilers were seen as translators. So it was a tool to allow developers to write in high-level code and generate low-level code automatically. That was the sole purpose of compilers. And this was good enough for back then, but then quickly the community realized that compilers are much more powerful than that. We can actually optimize the code. So developers often don't write the more efficient code for that specific architectures that we're targeting. So that's when we started developing the optimizing compilers, and this is the beginning of the second phase of compilers. In this point, the optimizations that were included in compilers were code-centric. What that means is that these optimizations detect patterns in the code using symbols and translate a pattern with a more efficient pattern, like the one you see here in the slide. And a lot of optimizations were developed with this mindset, and they're good, and they're still included into the compiler. So they're really good, and we don't want to throw them away, of course. But very quickly, we hit a roadblock in this mindset. And the reason is because we just don't use only variables, right? We typically use memory. And what that means in a language, you have pointers or references. So now the uniqueness here is that memory location, memory object don't have a symbol. What they have is a pointer. And multiple pointers may alias on the same object. So a simple pattern matching doesn't work anymore for this type of code. And that's when we started to have a third phase of the compilers, where I call it code-centric, driven by dependencies. Here, we still optimize the code with code pattern and replace it with more efficient one, but we use a new abstraction called dependence, which was introduced by Ferrante and group in 1987. And now we check the legacy or the correctness of a pattern matching algorithm depending on the dependencies. So the dependencies is a safety check to say if it is safe to apply a given optimization. And we are still at this phase, and there's nothing wrong with it. It's just like we found in my group that there is a roadblock now by using this mindset. And again, there's nothing wrong with this approach. Like including myself during my postdoc, I developed a parallelizing compiler with several advanced transformations called Helix, and here is me trying to debug some code with my collaborators, and we were able to implement it with this mindset. However, at the end of my postdoc, I realized that what I built, it took too long to achieve an advanced transformation. It took me 4 years, and the cumulative code base was like 100,000 lines of code. And that is just for transformation, that's it. So it was personally frustrating for me because it slowed me down in terms of testing research ideas. So when I started my assistant professorship at Northwestern, I decided to take a step back, and this was back in 2015. I decided to take a step back and try to think about if there is a different way of thinking that allow me to test research idea much more quickly, and therefore create more innovation more quickly. And this is what I propose, and this is what I call dependence-centric optimizations. Fundamentally, the idea is the following. We take the abstraction dependence that was introduced in the 80s, okay, and we make this concept first-class citizen. So now what you have is a bunch of dependencies creating a graph. And this is the input to the optimization. It's not the code. The code is a second order of importance type of aspect of the computation. Dependencies is the main central, it plays the main central role. And an optimization, it takes a dependence graph and it generates another dependence graph. As a side effect, automatically the code gets updated and the memory objects get updated. Okay, so if we focus on dependencies, code is not our input, and we manipulate dependencies to generate the code that better fit the hardware. Okay.
I have a question. Are those dependencies here mostly data dependence on the application, or it can be other things?
There are other things. So to be fair, to make this feasible, we had to take the concept of dependence that was introduced in the 80s and make it much more richer. And I'm going to talk about this today. Yes, because they're different. There is an entire heterogeneity set of concepts related to this. Yeah. Okay, so this is what I'm going to talk about today. Now, of course, we have to build this approach to understand how good it is. And there is no compiler that works in this way. So, and I didn't want to build an entire compilation infrastructure because that is a multi-decade type of effort. And so therefore we built a layer called Noel which provide the abstractions that we need, the dependent-centric abstractions and dependent-centric APIs you can use to optimize your optimization. And then Noel translates these requests down to a code-centric layer, which is an LLVM. So an LLVM is a compilation infrastructure that is widely used in both academia and industry, and Noel is a layer on top of it. So with Noel, we built roughly 32 advanced code transformations in 7 years. We published 22, and more are hopefully going to be published very soon. And these optimizations are organized in 3 different research directions. And one of them is that I'm going to talk about today is compilers for randomized software. So software where it implements algorithms that are randomized, like machine learning or Monte Carlo simulation. And I call it MARC because to give a tribute to the true source of randomness that I found in my life, the only true source of randomness I found, which is my son, okay, which is named Mark. And as Noel supports all of these optimizations, I call it Noel because my wife supports my obsession on thinking about abstraction. Actually, there is also a runtime I call it Virgin, which is the name of my cat. I don't have more than 1 kid, so I need to move more kids to do more projects. Okay, so this is what I'm gonna organize the rest of the talk. I'm gonna give you more detail about this dependent-centric approach, with the hope that you're gonna find it useful and accelerate your own research as well. And then I'm gonna describe the software infrastructure called Noel that implement these concepts. And finally, I'm going to give you an example of a transformation, a very advanced transformation that we built in the MARC project that rely on this dependent-centric mindset. Okay, first of all, of course, I didn't build everything by myself. Absolutely. I'm really thankful to all of my brilliant students that helped me in this journey, as well as I'm very lucky I found very brilliant collaborators that also became my friends. And students as well, and I was very lucky to see a very interesting idea that people come up with, very brilliant idea using this dependent-centric mindset. So I'm thanks to all of them. Okay, to describe the dependent-centric approach, I need to first describe what we use today. I call this code-centric approach. Here we describe computation starting from the instruction. So think about in LLVM, the concept of instruction in LLVM. So we have instruction and we have a binary relation between instructions, which is the successors. So most instructions have one successor, so which means after you execute one instruction, you will execute the next one. And some instructions have more successors, like a conditional branch. Now, this computation is described hierarchically. The lowest level is instruction, and then by taking advantage of this single successor set of instructions, which is the majority, they organized back then. They organized them into hierarchically into what is called a basic block, and then now successors go to these coarser-grained descriptor basic block, and becomes what we call control flow graph. And this is the way also compilers still work. And then also basic blocks get organized hierarchically, organizing them in canonical loops, which are not exactly loops in programming languages, but close. So you can see that is a hierarchical descriptor of the computation. So everything else is an afterthought. Okay, let's apply this approach to implement an advanced code transformation. One of the very advanced one is code parallelization, like Helix, for example. So one way to do it is, well, we realize, let's say this is a piece of code, which we're going to go slowly through it to see how we can parallelize this piece of code. And you can see this is not straightforward to parallelize. So let's say that we want to compile it and run it using conventional compilers like Clang or GCC or ICC. What you will see is that everything runs sequentially. And there's nothing wrong with it. It's just the fact that we don't have a single core in the chip anymore. We have many cores, and now they're even heterogeneous. So all of this extra hardware that we have and we're going to keep having, I think Intel announced recently that they're going to produce a core with 120 cores in a single chip. Okay, 119 will be not used. So that's the problem. We pay for this hardware, and we typically don't use it that well. And that's the issue. Of course, this is what I'm talking about. Client devices, and there domains where you actually have a lot of parallelism, let's say cloud computing, because you have parallelism across programs. But for a single program, for irregular workloads, let's say, think about your mailing system, like Outlook or GCC, it's everything sequential. Okay, so what we want to do is parallelize it. How can we do it? Well, first of all, we are one way to do it is, well, let's focus on the hot code. As long as we parallelize the hot code, we are good. Right? We're going to get good speed up. In this case, the hot code is the loop. So we don't care about the code outside. We only care about the loop. Let's parallelize the loop. So far seems rational, right? Let's do it. So, so the code outside runs sequentially. When we jump in the loop, let's imagine that we are a static code transformation. We want to understand how to parallelize this code to understand the complexity of implementing design. Okay. So first we start with the first instruction here, and we want to understand how many iterations this loop will execute, because, for example, we want to run them in parallel. So it's important to know whether the next iteration will run, so then you can start ahead, and therefore we can parallelize more. So here the condition is dictated by this variable here, I. So it's important to understand I. So parallelize the code. Now we switch to the concept of variable. Okay, let's see I. Well, I is defined by J. And by the way, this code pattern is weird. I agree. It's a simplification of a real bench. So, but this I is defined with the variable J. So now to understand I, we have to understand J. Okay, J is defined all the way down here at the loop, and is an increment of 1 from I. So, and I is then reused here. So you can see that there is a cycle of dependencies between these variables and this code, which is fine, we can understand it. And we can also realize that this is what they compose what is called as induction variable. It's a variable that you increment with a constant and known step size, and therefore you can compute with that closed formula the value of these variables at a given iteration without executing the previous iterations. This is a concept that I call fast forwarding. Okay? It's not something you can find in books, but this is the way you call it, and it's going to be obvious in a second one. Okay, so therefore we can actually execute 2 and 12 in parallel by doing this fast forwarding transformation. Okay, and it's not trivial, but it's doable for sure. So therefore, all of these different iterations will run on different cores by doing different fast forwarding of these variables, and that's good. Which means now the code transformation has to understand these variables. It's fine, it's doable. Let's go here. Can we run I3 in parallel across iterations? Well, let's see. We use Y and Q to define X. X is used in I5 to define M. M is used in I7 to define Y, and Y is used back in I3. You can see there is a cycle, again, of variables. In other words, it's a cluster of code that have to run sequentially, right, across iteration. That's fine, we understood it. We run it sequentially on A code. That's all. Let's go to I4. So now, to understand whether I4 can run in parallel, I hope you can feel the kind of a little bit the pain that I went through during my postdoc. So to run I4, now to see if we can run in parallel, we have to understand not variables, not code, object, in particular object fields. Because there is the code dimension, variable dimension, now object dimension. We have to understand them all. Okay? Now we have to understand this. Okay, here we read a field called H to define F, and then F is used to define a variable T dimension, and then this variable T is used to redefine F, which that means is that they create a write after read, write after write in this case, dependence back to I4. It's another cycle. Yes, you could run this sequentially, but you wouldn't do a good job, right? You can do better than this. How can we do better? By implementing an advanced transformation that realizes that this object can be sliced in 2 objects, an object that has the header H and an object that has an object with the field H and a different object with the field F. And because this new object with only the field F is written at the beginning of the iteration before you read it, then what that means is that you can clone it safely. Every core has can have its own private copy, and they can run in parallel, right? So we can do it. Let's do it. So they run in parallel. That's good. Then we also means we have to understand memory dependencies in order to be able to claim them. And now we go to I8 and we say, can we run this in parallel? Well, let's see. It relies on X, which was defined on a different cycle that we already have scheduled. So now we can see that this is like a corner case. It's not two cycles that they partially overlap. So whatever you choose has to be coherent. So this is an example of a corner case. So you do it by scheduling on the same place where you scheduled the previous cycle. So you have to handle a lot of these corner cases to be correct. And finally, we go to I10 and we say, okay, can we run this in parallel? It depends on the field F, which was defined by a different, with a green code that we run it in parallel, which is good. And then you use it to define L, which is used to update S. Of course, you can run I10 and I11 sequentially, but you wouldn't do a good job if you do that. You want to run as much things in parallel as possible. Here, we realize that the variable S is only used to update itself, which means the temporary values that this S will go through across iterations are not exposed, they don't leak, and therefore you can take S, privatize it, and then every core has its own private copy of S, which is updated with an associative operation. Then at the end, you take all of these private copy and you reduce them to a single one, and it's called reduction. So now we do reduction, and thanks to this, we parallelize 10 and 11. This is just an example. There are many different types of variables with different properties you have to handle if you want to really parallelize a large code base. And you have to do them all. And then if you do everything and everything is correct, you also have to understand control flows because this loop is relatively simple. There are no if then else branches, but if you have them, you have to understand them and how all this property changes when you have these control flows. Do you feel the pain? Do you feel how much you will suffer if you write a parallelizing compiler in this mindset? It took me 4 years to do this, okay? Okay, this is not the way to go. So how can we do it better? Well, so first of all, even worse, this is just about code analysis. You see the pain. But there is also the other side of the coin, which is code transformations. How to use this information to change the code coherently on multiple dimensions, like variable, object, code, everything has to be coherent with all corner cases. It's too much. 100,000 lines of code. And this is one way to parallelize the code. There are many, and there isn't a single one that dominates them all. So you actually want many to be in the same compiler so they can work cooperatively, like collaboratively. And there is no way I was able to take Helix and extend it and add more techniques on top of it. So I just gave up, take a step back, and I thought, how can we do better? Okay, it's a different way of thinking that will allow me to write this code. Would you agree that if I write this transformation that works on every code base you throw at it in whatever language you write, if I write this in 1,000 lines of code, will you be impressed? Right? 1,000 lines of code is a little bit bigger than looking back code motion in area. Okay. So let's see how we can do it. Yes. Yes.
Do you have an estimate of the cost of overhead and the analysis and the transformation?
Of compilation time? Yeah. Oh. If you do parallelization, you have to forget compilation time. It's a lot. However, if you compare against the alternative, it's okay. What is the alternative? You ask the developer to do it manually. Now, compared to the time the developer would spend to do this manually, the completion time that we get on doing this transformation automatically is actually much lower.
But an average developer and this transformation, who did better in terms of performance?
Actually, that's a great point. It depends. So let me say why I say this. So the best parallelization plan is architecture specific. So if you change the architecture, you go from Intel to AMD, you should parallelize the code differently. Now, imagine a developer that parallelizes a large code base in many ways, depending on all different type of architecture you want to target. And after you do that, you're going to have a high turnover in your company because people will hate that job. After you do that, now you have to maintain that code. That's really not easy, right? Now, imagine if instead you can do this process automatically, and the compiler is by nature aware of the architecture and adjust depending on the architecture, which is just a different cost-benefit model. Now,
Just more,
yeah.
What is the cost of also changing the compiler to adapt to a new architecture?
Actually, this is a great question. So it's not that much. A lot of these concepts that we need, not all of them, a lot of them, they can be parameterized for an architecture. So you can think about it as template programming. problems. Like you change the architecture, yes, you will have different costs, you will have different registers, you will have different latency and bandwidth with the memory. Those are parameters you use to instantiate your own parallelization. It's not that much. Okay, so let's do this in 1,000 lines of code. How can we do it? First we have to conceptualize what we did in a code-centric way to understand what to change. Let's conceptualize it. The code will go to a variable analysis that understand which one are reducible, which one are induction variable. Then it goes to the control flow analysis, actually quite a few of them, to understand all different control flows. Dependence analysis to understand memory dependencies. Object analysis to understand how we can change the objects, which of course will rely on dependence analysis. And all of these, which is different descriptors at different dimensions of the computation, go in the code-centric transformation that now has the hard job to understand them all together and then change the code accordingly. And this is the problem. This is blow up the complexity at this stage here. Okay, instead of doing that, the idea is to try to take all of these different aspects of computation and map them into a single dimension. So then the code transformation only think about a single dimension. Okay, so this is the dependence-centric approach that we have been developing and using for every paper since 2016. Okay, so the code goes to the dependence analysis, and the output is a richer descriptor of the concept of dependence introduced in the 80s with more information about the nature of that dependence. Then this one, just the dependencies, not the code. The dependencies get translated down to dependence-centric analysis, which take these dependencies and organize them hierarchically, like the code was organized hierarchically, let's say in LLVM, GCC, in every compiler, instruction, busy block, loops, function. Here we do the same thing, but for dependencies. We're going to see how we do that. This one generate a bunch of dependence-centric abstractions that describe the computation in different granularity, following the dependence-centric approach. And then these and only these abstractions go inside the transformation that the only thing it does is take this graph and manipulate it. This is a hierarchical graph where the hierarchies in the nodes and on the edges, and I will understand that briefly soon. And then you generate the code as a side effect. So you can think about the dependence-centric abstractions to be a view of the computation. Okay? There's nothing else. You don't have to understand variable, you don't have to understand object, you don't have to understand anything. You just have to understand dependencies and how they're organized and their properties. Okay. Let's apply this approach before I tell you what is exactly on to do the same task, parallelize the same code. How can we do it? Okay, first of all, we go to dependencies. So which means the code disappear. Now we have a bunch of dependencies. And so it's a graph. Okay? Then we go to the dependence analysis to create the following abstraction that I'm going to build step by step. But then the ultimate result is what you get out of this process. So first of all, we recognize that there is a strongly connected component. So this is a concept that we borrow from the graph theory. So a strongly connected component is a subgraph, or is a set of nodes that have the connectivity property, which means you can go from any node to any other node following the edges. And second property is that this is the maximum set of nodes that hold that property. So if I add any extra node into the mix, I will lose the first property, the connectivity property. These define the strongly connected component in graph terms. This is a strongly connected component, which is not a cycle, it's richer than a cycle. Okay, which means we now start organizing these dependencies hierarchically by clustering these into an SEC, strongly connected component. Then we also reorganize the edges, creating a hierarchy of edges. Now we have an edge that connects strongly connected component, which has sub-edges. To explain why this edge exists at that granularity, go down into lower level if you need to. This is another strongly connected component, which we translate and which we organize in this way. But this is a spatial strongly connected component because it has the clonable type. What that means is that you can take this SEC and you can clone it. Why can you clone it? Is because it's a different way of satisfying these dependencies. Okay? Now, in order to identify these, we have to understand where these dependencies come from and what is their property. So let's zoom in a little bit into it. So first, there is the code analysis. This is for the system to do and to be able to provide this concept of clonable SEC. So here we have to identify whether this SEC is clonable or not. If it is, the transformation can ask to clone and as many times as you want, and put them in as many tasks as you want, and therefore they will be mapped into. So this is, and it has to be, of course, correct and conservative. So if we detect an SCC to be clonable, it has to be true. Okay. It also means that you expose a capability of this SCC. It's a degree of freedom that now the transformation can use to accomplish a given task, let's say a parallelization, a vectorization, or something else. So here, all of the transformations required to clone the SCC, the transformation doesn't have to understand. It just asks, I want to clone this SCC and put it in this task or put it in this function, it doesn't matter. The system will take care of the detail. All of these code analysis and transformation are definitely complex, but they are not optimization specific. We are providing concepts that then the transformation will use to accomplish a task. In other words, the line of code that the optimization specific is significantly lower. Okay, this is the clonable SCC. Then we identify another SCC. This is about the induction variable. And as you can imagine, now we have a different type of SCC, which is the induction variable SCC. The capability of this SCC is to fast forward. So you can take this SCC and say, I want to have this SCC, I want to instantiate this SCC at iteration 5. Okay? Or I want to fast forward 5 times. For whatever is your reason, it doesn't really matter for the system point of view. The optimization has to know how to do, like how to manipulate the dependencies. The system ignored that. It just exposed capabilities. And then we have this SCC, which is of a special type, again, reduction. Now, the reduction SCC can be cloned, but then at the end, you have a cost of reducing all the variables. That's really the main difference. It has the same capability of clonable, but the cost is higher. Now, when you have these to be the input of a parallelization, the parallelization, which before was very complex, is now a scalar. You really look at this and you say, how can we parallelize this code? Well, let's see. First of all, we have these SCC. Well, we can instantiate as many times as we want. It's fast forwardable. So we want to maximize parallelism. That's what we do. Now this one has no capability. It means we cannot do anything. We just literally have to copy somewhere, and that's it. So we put it in core 0. SCC1 can be cloned as many times as we want, and we do it, as well as SCC3, and we parallelize it. And the system, so you literally just map and use actions or capability that SCC has to do whatever you need to do. And the system under the hood, it of course keeps track of the changes you request and change the code and the memory objects accordingly. So all the complexities now shift to the system, to the compilation infrastructure. Okay, so these are the 3 types of SCC, and I really like that at some point I wanted to understand how many of these capabilities or how many different types of SCC we have in modern workloads. And we started to organize them hierarchically and kind of like being in a hunting mode to try to find them. And we found something very interesting. Not only there are a lot, but they are highly organized conceptually. So remember clonable SCC, for example, you can have it as a stack object. And if that's the case, when you clone it, the overhead is going to be lower. Or it can be a heap object or global object. You don't have just an actual variable, you also have wrap-up variable, flip-flop variable. If you're not familiar with this concept, that's fine, don't worry. It's just like there are different instances of variables that can be fast-forwarded just in a different way. And all of them have in common the fact they have a closed form to apply, and they're recomputable, and they have a loop carried. So not only these concepts organized well or hierarchically, but also by when we implement them, we can reuse a lot of code. Because every time I need to have a way to recompute it, I put the code here, and everything here is mapped into C++ classes, so we reuse the code. Okay? And it's not just this, we have a lot of concepts actually, so much that they don't fit in this slide. So I had to zoom out a little bit. And we have even more here. And these are just the ones that are in the current stable version of our system. We actually have more coming. So they're really nice as they expose capabilities to the user, and they're very rich and organized hierarchically, which is something I honestly was not expecting. It seems like quite interesting. Okay, so now thanks to these, yes.
Just to the prior slides.
Yes. Oh, sorry. Yes.
The one.
Zoom in.
No, the methods that you presented.
Oh, then the methods is this. You can. This is the methods. This is
Okay. So it is like static analysis in the beginning.
Thank you. There is nothing fundamental that blocks us to stay at static time. However, what we built so far is static time.
Okay. And my question is like the overhead that you have in your system is slightly different than the one that you have in the traditional one.
What do you mean as overhead?
I mean, completion line.
Okay. Thank you for the question. So the overhead is actually very similar. And the reason is because the compilation time is dominated by memory alias analysis that power both approaches. So, and that is independent, which is whether you choose code-centric or dependent-centric, because that is the dominating factor. The compilation time is the same. It's just here with the reorganization of dependencies and creating this hierarchy of SEC, it doesn't cost nearly as close as what alias analysis.
So also like to parallelize your code, for example, it is very sensitive to the way the program runs.
Yes.
Also, the challenge that is taken, the different flows can be highly affected by dynamic behavior of the software based on the input variable, for example. It can be,
yeah. It can be. However, there are solutions for that. You can do cheating or you can do code versioning. But my point is that these advanced transformations are needed, even for vectorization or pick your goal. And if you implement them in a code-centric way, it's going to slow you down to actually test that idea. If you go to the dependent-centric way, it's going to take you like significantly less time and line of code to actually test it. So that is, the way I see this approach is an accelerator for research. And I truly see the need to significantly boost innovation in code transformations. And I think dependent-centric could be a good solution for that. So that's the mindset I use when I, that makes sense. Yes.
Yeah, so there are a lot of boxes involved sites.
Yes.
But we only see the reduction from code-centric values to dependent-centric values.
Yes.
Is there any, these like, how does the end-to-end?
Thank you. Thank you for the question. So roughly, so first of all, notice that all of this part, which is going to be the dominant factor in terms of code size, is optimization agnostic. So therefore, if you have, let's say, in our case, we have more than 30 advanced transformations, this cost is shared across all of them. So that's why I emphasize on this aspect, because that's really what really matters. If you want to have innovation, you want to build these once and then try idea and then try many of these optimization, so then you can create innovation faster. But in terms of total line of code, so far the overall system we built is roughly 60,000 line of code. A little bit more now, like 65,000. And then Helix, for example, is 1,000. But now we have more than 40 advanced transformation, and each one is roughly 1 or 2,000. This one that is, I think, like 45. And now, if all of them would have been implemented in this way, I would not be here talking about them because we're not that concluded. That's good. Okay. So thanks to this, we were able to build the first compiler ever designed, ever implemented, that has Helix parallelization, dual parallelization, DSWP parallelization that work under the hood all together collaboratively, which means you have different way of parallelizing the code, which are basically different scheduler of SEC. And now you can decide to parallelize one loop with one technique, another loop with another technique. You can even take a loop and parallelize in many different ways, and then do code versioning and decide which one to jump to. And you can do this now. And this was definitely, I would never have dreamed to have this if I followed this approach. Okay. So, but overall, this is the dependent-centric approach, which again is parallelization agnostic. It just provides capability. And we implemented a lot of transformations that have nothing to do with parallelization. So let me jump into Noel, which is the incarnation of these concepts. Okay, so Noel, it extends LLVM to create a layer of dependent-centric abstractions and API. So Noel was published last year in CGO, but actually the development started in January 2016, 3 months after I started my pre-tenure journey. And every year we add more and more abstractions that are more and more on top of the dependencies and more richer representation. And there are more abstractions that are coming. Noel is a very active project. Right now we have several research directions and several groups that rely on Noel. And just to give you an idea, I'm not the solo developer of Noel, of course, but just myself, I think I roughly 80% of line of code I write every day, and I do write every day, is on Noel. And this is my GitHub activity. You can see it's just me makes Noel active, and I'm not the only developer. So this is going fast paced. I think we're reaching a kind of a plateau right now, which is fine. But yeah, it's a very active project. Okay, so what is Noel? So let's take a step back and let's refresh our memory on how compilers are organized since the 80s. And this is, of course, it's something you learn in every compiler class. So sorry, I'm going to go quickly. So we have the front end that takes the source code and translate it down into a code-centric IR, structure-based objects, etc. Then you have the middle end where you have the majority of the optimizations, okay, the one that we want to accelerate in terms of developing. And then you take the optimized IR and use the backend to generate the binary. So this is where we focus our attention, the middle end. We want to write advanced transformations in the middle end as fast as we can. How these transformations are typically organized for if they are advanced. Typically, you have a bunch of code analysis that generate an abstraction, one or more abstraction, and then the transformation uses this abstraction and the code to change to apply the optimization technique. For example, in LLVM, let's say that for whatever reason, I want to swap INJ, these two instructions here. How can I do it? Well, first of all, I need to know that this is a safe operation. Will I preserve the original semantics if I do the swap? Well, in order to understand that, I need to understand whether these two pointers, P and Q alias, so could they point to the same memory location at runtime, yes or no? If the answer is yes, I cannot swap them. If the answer is no, I can swap them. So because of this, LLVM provides an abstraction called alias, which is a binary relation between pointers, and implement this, and this is fine. We start from this. This is good. It's a good starting point, but it's not enough. Now we build upon it and creating a rich set of dependent-centric abstractions that look at the same property of the code from a different angle and different organization. This is the way Noel is. It's literally a layer on top of LLVM without hiding LLVM, because it is important that to embrace the fact that when you build a dependent, even when you build a dependent-centric abstraction with that mindset, dependent-centric optimization, even when you use that mindset, sometimes, especially towards the end, you might want to do some transformation that are relatively simple that require code-centric abstraction. Sometimes you do that. You need to do that. And that's why Noel does not hide them, just complement them. So you can write a dependent-centric transformation in our framework, use the code-centric API in LLVM. We're not hiding them. We're not blocking them. You can do it. You don't even let us know that you did it. It doesn't matter. And then when you do need a dependent-centric view of the code, then you ask Noel, give me this abstraction, the SCC DAG code, the DAG created by connecting the different SCCs and their capability. And Noel at that point run the analysis needed to generate that abstraction, and therefore you pay the completion time of it, and give you back that abstraction, which now you can use to decide what to do. After you decide what to do, you probably want to express the changes at the graph level, at the dependence level, not at the code-centric level. That would be insane. So therefore, you ask Noel, do this transformation of these, like clone this SEC. And Noel internally take this, understand which abstraction is needed to implement or fulfill this dependent-centric request, and translate it down into a lot of very micromanaged set of low-level code-centric API that LLVM provides. Okay? Does this transparently to you? And then with this, we developed, again, around 30 transformations, and 22 are published, and more hopefully are going to come before the end of the year. Okay, so this is Noel. We built 3 research directions. Because I found this very useful for us, and I decided to start creating tutorials. Not well done by any means. They are meant to replace documentation. I don't like to write documentation. This is a replacement for that. So on YouTube they're there, and I'm gonna produce them. I just started like a month ago. I'm gonna keep doing that until the summer. My hope is by the summer everything is there. Okay, so here we built a lot of analyzing compilers, studying. We were able to quickly test research ideas with this approach, and we published them in compiler venue or compiler and architecture venues. And here we study different way of thinking about speculation and different way we can put together speculations to lower their cost. How to change the granularity of the execution unit that execute on a given course for granularity control, and a different way to take the parallel code and make it more coherent with the OS API, so then you're not blocked by, for example, I/O or these type of things. And finally, how to take the parallelized code, and for whatever reason, you might want to map it and run it in kernel space rather than user space. And how to do that, or how to parallelize the code when you don't start from C and C++, but you start from, let's say, OpenMP. Like, how can you, what is the way to do that? And all of these have been done in relatively few years because we focus on dependent-centered transformation. And this is just one research direction. So, and of course, also there is another work that we recently published that generate not the binary, the parallel binary, but we generate OpenMP code that looks natural to the user. Okay, now let's go for an example, deep dive into an example of advanced transformations that in the MARC project. So, okay, in MARC, what we did is this. There are different transformations that we implemented and published, and they look superficially to be different, but fundamentally, that's what we did. We took the SEC hierarchy of concepts that we saw before, and we extended them with new SEC types that are specific and with specific capability for randomized algorithms. And we found that there is one that is we call state SEC, which we heavily exploit. Now I'm going to talk about state SEC, but before, why do we care about randomized algorithms or randomized software? Because there is a lot of emerging workloads that do require randomization. For example, multimedia analysis, you have a video, you want to detect where the parts of the body of a person is or the face of a person. In order to do that, you have to encode in the software the unknown, I don't know where the body is, and you implement it typically with a distribution belief. And you implement that with pseudo-random value generators. So you generate pseudo-random values, and you organize them following a certain statistics that you know to be true in your domain. Monte Carlo-based algorithms are generalization of these concepts, which are done in many domains. Okay, also machine learning use randomization to avoid getting stuck in the local minimum, and streaming computation use randomization to scale down the computation to match the speed of the incoming image. Okay, so this is what we fundamentally are. We use this state SEC that we're going to exploit to do fundamentally one thing, which now I'm going to try to conceptualize. Let's see if I can do it. Okay, let's imagine that this is a conceptualization of an execution of a program. Let's imagine on the x-axis is execution time, and let's imagine that on the y-axis we take all possible program states this program can be in. Program state is the union of the values of all registers and memory locations, and we organize them in a way that makes sense for that program. We start the execution at 0, 0, we let it run, and if the program is deterministic, the execution of this program will go through this space following a path, right? And if I run it again, and there is no bug, and there is no data races, there is no undefined behavior, then the execution will follow the same path, exactly the same path if the input is the same. This is the deterministic program. But if you have a randomized program, or a non, which is a type of non-deterministic, now with the same input, without any bug, without data races, you're going to go through the space following a different path, which is fine. What we found is that these paths intersect. So let's look at this intersection and let's see what this means. You can slice now this space into before and after the intersection. Forget about the after for a second, focus on the before. The fact that they intersect creates a degree of freedom that wasn't explored before. Because now we can reach this state following different paths. And some path might have more parallelization, some path might have less memory footprint, some path might have more vectorization. Choosing which path to take to reach this point can be very interesting to exploit wherever is the current state of the machine to fully utilize the hardware. That's fundamentally what we're doing. Yes.
Any chance they don't intersect at all?
Sorry?
Any chance they don't intersect at all?
So theoretically, yes. We never found one. But theoretically, yes. I think the reason we never found one is because this, again, this is a speculation on my end, is because the developer embraced the fact that you potentially have a divergence in the evolution of the execution, and you want to control it. And by controlling it, you're putting some guards or something, which force this path to basically increase the likelihood they intersect. And they do intersect. Now, of course, the problem is that you don't know when they intersect, and that's where what I'm going to describe is going to focus. So in general, what we found is that even if all compilers satisfy all actual dependencies that actually materialize at runtime, so they actually require data movement. I think about a producer-consumer type of relation with left or right. Like what we found is there is a subset of actual dependencies that can be satisfied without sequentializing the code. Okay, we call these state dependencies, which is the dependence granularity concept. And now when these get to the SSE, it becomes the state SSE. Okay, to explain what is this concept, let me use this in a bench body track. In body track, this is a benchmark of the part suite, but you can apply this to any Monte Carlo simulation scenario, or actually even more in general. Yeah. Every time you have a stream of computation or some kind of evolution. Okay, so the task is you have a video, and actually to be precise, you have 4 videos that are captured by 4 cameras placed in a specific place that capture whatever is going on a 3D space, let's say an office. And the task is to take these videos and tag it and generate a new video where you outline, you highlight the borders of the different parts of the body of a human for every human you have in the video. In this way, you can better track if somebody is touching something or not, and things like that. Okay, so this is the task. Now, the algorithm, I have to say, is actually very well implemented because it exploits in the fact that we are not superhuman. What this means is, if we know magically that the body of a person, let's say, is right here, we know that the frame after, the body is going to be in the surrounding area, right? We're not superhuman that we jump around like crazy. The algorithm exploits this to generate a relatively low computation algorithm and have a very high accuracy where the body is through time. This is great for accuracy and keeping the computation low. This is fantastic. It actually is really well done. The problem is we now have created a dependence, state dependence, that sequentializes the whole thing, because we have to take the knowledge where the body is and propagate it to the computation of the next frame. Now you have millions of frames, right? If you have a video, and potentially infinite set of frames. Now we sequentialize everything. So that's the problem. And the dependence is about updating the state of knowledge where the body is. That's why we call it state dependence. And therefore, you run sequentially, and now you don't take advantage of the multiple cores. But we make the following observation. So it is true that where the body is at the given frame depends on the previous frame. That is definitely true. But is it true also that it depends on where the body was a million frames ago? In other words, where the body is, where I am right now, does it depend where I was a year ago? A year ago, I didn't even know I was going to come here and give a talk. There is no way, right? So there is something here. There is something that is like some kind of short memory property, right? It depends on some few frames before, but not all of it, okay? In other words, the assumption is that this is a Markov process, right? If you are familiar with machine learning concepts. Okay, so therefore, let's say that I know exactly what is the length of this short memory property. Let's assume we do. Typically you don't, but let's assume we do. How can we parallelize this code? Well, we can chunk it. Let's say we know the length is 2. We can chunk all of these frames, and then the only problem is to the computation of the first frame of each chunk, with the exception of the first chunk. So now chunk 3 requires the state that will be created by processing 2 and 1. Right? That's the length of the short memory property. So now what we can do is append an alternative producer that it doesn't generate any output. The only thing it does is warm up the state. It's like warm up in the cache on a simulator, an architecture simulator. You warm up the state, and you pass that state to tree, then now it can actually run and generate the output. Now you might say, well, but now you're creating way more computation, and that's definitely true. You create more computation, but everything running parallel. So now we translate. Think about what we did. We translate an inherently sequential algorithm into an embarrassingly parallelizable algorithm. Right? We went from one extreme to the other extreme, exploiting this short memory property. Good. But the problem is that we don't know the length of the short memory property. Therefore, we are speculating on it. And we have to treat it like that. It's a speculation. So when we generate a state from the alternative producer, we compare it with the original state that at some point we're going to have. And we treat the execution of the chunk that is in speculative mode. Then when we reach the two states, we check, do they match bit by bit? If the answer is no, but if the answer is yes, great. Okay? Typically, they don't. So, but now, the reason why they don't, it could be either we were wrong, the length of the short memory property is not true, is not whatever we think, or it just there is no short memory property to begin with. Okay, either we were wrong, or we simply embrace the fact that this is just one of the possible correct original state. Let's not forget, this is a randomized algorithm. So therefore, we run it again and again to have a set of correct original states that the original algorithm have declared to be correct. And now we just have to check if the speculative state match any of them. And if we do things right, this is typically yes. So with this, we now can guarantee correctness while we speculate on the length of the short memory property. Now let me show you the impact of this. If we run this program sequentially in one core, it will be 1x. Okay? Now, if we use 28 cores to run the parallel version of this algorithm, we get 6.5x. And I have to say this, I'm kind of impressed about it. It doesn't look big. I'm really impressed about the 6.5x because the parallelization that is exploited is in the computation of a single frame. Now, think about it, the computation of a single frame is not that much. I mean, the algorithm is designed to reduce the computation load of a single frame. So you don't have much to parallelize to begin with. The fact that they get an end-to-end speed up of 6.5x and use 28 cores to do that, I think it's impressive. And now look at if we use our parallelization technique, we get 21x. And we don't get 28 because there is a cost, which is the alternative producers, that we pay. But that cost, it overlaps across chunks, which means if we double the number of cores, we're going to keep scaling as long as there is an input, right? So now you can say 21x is good, but what does it mean? Do we need 21x? That's a good, healthy question to ask. Is this a speed that we actually need? I claim yes, and let's see why I'm saying that. Here you have the input video of body track. This is the output video of the binary generated by Clang 03 with the full set of optimization, MR native, so literally the best of the best that Clang provide. And this is instead the binary we generate with our infrastructure and everything. Look at this. Look at how slow this is. It's kind of sad. Look at this. The reason why we go at this speed is because we are bounded by the speed of the input, which means now we can actually scale up the frame rate here, and we will still probably be usable live for the first time. That's pretty cool, right? Okay, so this is stats, and we have other transformations we built using this concept. That applies more specifically to machine learning, in particular training, which is a big deal. It takes a lot of time, or selecting the right pseudo-random value generator. So now to be actually a very good idea, you should change pseudo-random value generator depending on the architecture. It's actually is a fact that it was unknown before. And last bit of work we did with Paralysis that automatically generate programming language abstractions for you, let's say OpenMP pragmas or smart pointers or things like that. And for randomized code, we automatically generate the code that we need for stats, okay? Which is, I didn't mention, but stats require an extension of the C++ language, and we automatically generate that with Python. Okay, so this is Mark. We have another research collection. Unfortunately, I don't have the time to talk about, but is a set of advanced transformations that focus on low power device, like intermediate computing is an example. Their energy is the king, is what you have to optimize, and we can actually optimize quite significantly, even up to 45–50% energy reduction by just completely transparent to the user, optimizing the code in a different way. This is the papers. Overall, this is what we built. I hope I convinced you about the value of a dependent-centric approach. Please take a look at the videos, try to play with Noel. Let me know if that accelerates your research agenda. That's the purpose. Again, that's really the purpose of this talk, is to see if others will take advantage of this new way of thinking about implementation. It might accelerate the rate of publications that you will have. I really hope it will be the case. With this, thank you. Any question? Any question is good. Yes.
Question. So Stats is a compiler. Is it specially wrote for this particular application? Who's brought it to write this compiler?
Thank you for the question. It looked like that, right? Because yes, it's because it was. I was trying to use a benchmark to explain why this works in the way it works, but no, it's not benchmark specific. We actually target pretty much every parsec benchmark. We speed them up. There was one benchmark we didn't speed up, which I think it was really interesting. It was fluid animate. So in fluid animate, you run the code and you simulate the fluid that goes through a channel tube. Now, the reason why we didn't speed it up is because it's not randomized to begin with, and there's no data races. But we included that in the set of experiments to understand if someone misused stats, use stats to optimize a benchmark that is not randomized. What will be that cost? And we found that, yes, you pay a little bit of overhead, but it was, I think, around 10%, if I remember correctly, 5 or 10%. So it's not too bad. And if you don't see speed up, you can turn it off, the optimization, if you want. You can even plug an auto tuning and say, did the speed up? No, okay, turn it off. But yeah, no, but it's not benchmark specific. It's more general than that. Does this answer your question? Oh, you're not. Yes, right now. I don't believe you.
I was just thinking about then. You have instead of having a compiler for each particular program, you have a compiler for each program class.
I would say a compiler for workloads that are randomized. Yes. Yes, if something is not randomized, I don't think stats is the right answer. Yeah.
You have like a super compiler which determines which.
Yes, absolutely. We don't have it, but yes, absolutely. You can put an auto tuning on top of everything, and you can think about stats to be like another transformation you put in the mix, and then the auto tuner play the toolbox and pick up the right set of transformation, and stats will be one of them, and we'll see no impact, and therefore we will disable it. Yeah, absolutely. We didn't do that though, but yes.
So first of all, thanks a lot for your talk. It's very interesting. So have you also considered these platforms for hardware beyond CPUs, like GPUs?
Great question. Yes, and working is in the process. Hopefully, it's going to be published before the end of the year. Right? Yes, absolutely. It will go beyond even GPU. We'll also touch on this.
In the optimizer dependent-centric program, sometimes you say that generate a new code. This new code still have the same security damages. They still pass the same test that the prior level did.
Great question. So the answer is yes, but it's yes only if the optimizer does the right thing. So, for example, you still have the concept of dependencies, and the optimizer might decide to ignore independence for whatever reason. Like for example, because the optimizer is a graph translator, basically. You can take a graph which is correct, and if you satisfy everything, is going to be correct. And if you use the capability and only the capability expressed, it is correct. But you can change the graph. So you can decide, I'm going to remove this dependence for whatever reason. Now the code you generate afterward is going to be incorrect. So the security, the correctness is as long as the optimizer manipulate the graph correctly, in the sense that you follow the graph. But if you think about it, it's the same as code-centric optimization. You can change the code. Will the generated code be correct as long as you change the code correctly? But that is the issue in the code-centric way, because to know whether that's correct or not, you have to think about the code, the control flow, the variable, the memory object, all of these dimensions all at once. That is the same at a very high level problem.
But the process is always deterministic one. If you give the same input, always the same input.
So you're talking about the dependent-centric approach, or you're talking about stuff?
Depends on the
So what is deterministic?
I mean, you give one input, the end generated code is
Deterministic is the code. You're talking about the if the input is a deterministic code.
no. Given one input, you always have one output. Have anything there.
What is the input of a compiler is the code.
Exactly.
So, you're saying if it's going to be it's deterministic also in the dependent-centric approach. So if I rerun my optimizations on a given code, I will always have the same code. Yes. Yeah, absolutely. Unless the optimizer, which is something we didn't explore, probably is a bad idea. Unless the optimizer is randomized itself, then which you could do it. Maybe it's not a good idea. Yes.
For parallelizing compilers, how do you handle debugging?
Debugging what? The program, the binary, or the compiler, or the transformation?
You run the program and it's the same issue as like when you have a processor and there's no reorder buffer, right?
Yes.
Here it's like the code is duplicated and it runs on multiple cores.
Yes.
If I run that code and I get an error, like, will I understand the error? Like, how do you manage that?
So, okay, this is my personal experience. A parallelizing compiler will help debugging if the alternative is write the code in parallel.
Oh,
Here is the reason. If you write the code in parallel, you need to fully embrace the parallelism in your debugging process, which is really complex. That's why there are tools that try to help you, but it's very complex. If you have a parallelizing compiler, your input is sequential code. Now, you can debug the sequential code. And if the sequential code is correct, the parallel code generated by the compiler is going to be correct. Right? It's a good way of, like, this is, in my opinion, the strength of having a parallelizing compiler of sequential code. Said that, if the parallelizing compiler takes as input a parallel code, now you have the similar problem of debugging a parallel code. Yes.
I was going to ask if there are any formal guarantees for that transformation you put, or is it more like a trial?
No, it's a formal guarantee. Yeah, it's similar to code-centric transformations. As long as you satisfy the dependencies, it's going to be guaranteed to be correct. Same thing here, dependent-centric transformation. As long as you satisfy the dependencies, and so therefore you transform the graph in a way that satisfies the dependencies, everything is correct. Now, this is, of course, this is not something you read a lot about it, but satisfying all dependencies guarantee you to have correctness, but is a sufficient condition. It's not necessary. So there are some transformations that will not satisfy dependencies and still be correct. We don't have those in any compiler today, code-centric, as well as no in the dependent-centric. But this might be an interesting research traction to look at. Yes.
How naive is OpenMP compared to parallelizing compilers?
It depends on who you talk to, I guess. In my experience, so again, I've read a lot of code, and of course, I want to use my multiple cores. So I write OpenMP. It's not typical, it's not like a daily thing I do. I write typically C and C++, or C# when I'm lucky. I love C#. So in my experience, OpenMP is good to give you some speed up, but is not close to what you can achieve with today's and to achieve that speed up, you actually have to do a lot of tuning. You have to play with the attributes of each pragma to actually do it. And that will give you maybe, if you're lucky, half the speed up of the number of courses you have. If you want to go beyond, I think you need to do something else. OpenSilk is a good alternative, actually. It was rewritten by the authors of Tapir, and it actually is surprisingly good. It's actually very good. But I would argue that the complexity of writing OpenSilk code is higher than writing. There's a different point in the space. Yeah.
So when it comes to like developing this software itself, taking place a lot of like parallel conversions, such as load balancing, thread pools, memory pools, and so on.
Yeah.
Is this platform aware of all these opportunities and
Yes.
try to tackle them?
That's right. There is actually one set of transformations that we have that change the allocate or the cluster allocations. And then yes, these are type of SCCs that you can leverage. And you have to do that if you want to generate efficient parallel coding. Those are not optional. You have to do it.
One question, do you
Yeah.
have any, what workloads are most used in the platform? Is it like the performance or benefits that you gain is workload dependency somehow?
Oh yeah, absolutely. Like how much speed up you get out of these tools. Yeah, it depends on factors like the algorithm that is, if that something is fundamentally sequential, unless you have stuff that is a collect like a special case, yeah, it's must be sequential. The good thing is that we found a lot of parallelism that is in the code, especially it's quite interesting. It seems to me, again, we didn't do a study of this, but like, at least in my personal experience, that is probably biased in the software I went and did a dive in debugging. The larger is the code base, the more inherent parallelism is in the code, trapped in the sequential code. And probably because it's much harder to, again, this is my speculation, it's much harder to parallelize for a developer to parallelize the code if the code is big and complex. And therefore, you only parallelize the most obvious things. And a demonstration, an empirical demonstration of this can be seen as if you take the last spec benchmark suite, spec CPU 2017, some of them are parallelized with OpenMP, but if you look at the speed up you obtain is single digit. And these workloads are complex. And you can do better.
There is another aspect of parallel coding, for example, that affects most developers is when it comes, for example, I think like what is wrong, but what I saw here must be like prime parallel opportunity and then divide it and run it in parallel.
Yeah.
But there is other issues that sometimes you cannot avoid depending on the behavior of the program itself. For example, when you need to synchronize your code.
Yeah.
And so we have a lot of trade-offs like in the real world with the programs like between correctness and optimizations. For example, if you talk about atomic, for example, variables. So most developers are afraid of using like more relaxed atomic variables and basically relaxed in C++ and many others. So can somehow this platform use this very low level parallel synchronization primitives better than software developers?
That's a great question. This platform does support that, and we actually use it. Can that be better to what the human can do? In my mind, whatever the compiler can do, the developer can do as well. However, it's just a matter of cost. How much cost will it take a developer to do that and maintain that code? Like often maintenance is not taught, but is a major cost. So you want to write code that is maintainable. And if you start to doing line assembly or do all sort of kind of versioning, depending on that code is not maintainable. So if you're willing to have a non-maintainable code, then I believe the developer will be able to do it, but that code will not survive. I think in the long run, the compiler can do better for the developer because of this. And you do need to use that, yes. Also, parallelization on this aspect, when you do synchronization, there are different ways of synchronizing it, and there are different trade-offs there, absolutely. And they are architecture specific. That's why the compiler should do that rather than the developer. Also, let's say you pick a certain trade-off, latency, let's say, of a given synchronization mechanism. The way you parallelize the code affects how much of that latency is exposed in the critical path. And this is another aspect that is hard to think about as a developer, but the compiler can do it. So that's another aspect that makes everything much more complex. And we do it.
When I say developer, then there are the tools mostly average programmers. Like
Oh, then the answer is an easy yes. Yeah, absolutely.
People different.
Yeah, of course, of course. I mean, if you think about, we have been in the multi-core era for like almost 2 decades, and your laptop, my laptop, your phone, my phone, most of the time, most of the cores are not used. That's an empirical demonstration that the average developer is not good at writing parallel code because it's just hard, right? Think about, like, I don't think as humans we are good at thinking about parallelization. I don't think that's the case. Maybe wrong here, but I am not.
I don't think humans are getting better software anyway.
Yeah.
I think as it becomes old and larger, I think nobody can that.
Yeah, I agree. And I think there is a concept. One of my students told me used this concept in one of the talk that he did at my group. He said, write only software. You write once and you hope nothing breaks. And if something breaks, you patch in something that you don't know if it is correct, you don't care. Yes.
But more one question.
Sure.
You have an heterogeneous system.
Yes.
Let's say even CPU based on.
Yes.
Can you somehow, based on the feature of the adapt your system, for example, to choose which particular part send to which particular core?
Yes. So yes, and you should do that. We don't do it, but there is a line of research that we don't do it, but is very I think important that it should be that should be done, and that approach should be combined with the runtime that you have in the Paralysis, that you generate and link with the parallel generated by the compiler. Then you need to have some kind of task engine, some kind of runtime that decides exactly what to do. And even more ideally would be the compiler would use a richer cost-benefit analysis that take advantage of the full heterogeneity that you have in the hardware. Absolutely. We didn't do it, but yes, the answer is we should do it. Yes. If you're interested and you want to have, yes, that's a very good direction, right? Nowadays, everything is heterogeneous. Even the Intel multi-core chip, like it used to be always, every core has to be the same, and now it's not. It's like the big leap of this architecture. It's another example of how the hardware is becoming out of control, honestly, like super complex. And it's needed because we need performance, but that complexity shouldn't be exposed as is the problem. That's my personal opinion. That's why compilers will save the world. We just need innovation in the code transformation. That's why we build it. I truly believe that.
So do you think, for example, these can also, for example, there, I just said, like here, like heterogeneity between CPUs and the same system GPUs now are being worked, for example, could be also leveraging techniques to future or to particular section of the code and stick to a particular functional unit instead of the system.
Yeah, absolutely. Yeah. You probably need something. You probably need some kind of architecture descriptor that exposes this functionality and capability and costs to the optimizer you write on top of Noel. Yes, but and yeah, there is no need. There is no reason.
My final question.
Yeah, please.
So we have a lot of security implications of such systems today.
Yes.
For example, could you describe a bit about the role of compilers in this aspect? For example, if the compiler puts some sort of detect statical analysis program attack, for example, if you know that a particular region of the code is being accessed multiple times, could the compiler somehow detect that at completion time? Detect that?
That is a great question. So we don't know each other, right? We didn't set this up.
No.
Ready, good? Okay. Recently, we published a paper in that one. In particular, it was of a static analysis to try to do exactly that, try to understand if there are possibilities of attacks on a certain code base. And of course, it's conservative, right? It might say yes, it might not be true, but yes, you can do that. And now the type of attacks that we tackle depends. I don't know if we can handle all of them. I'm not a security expert. And by the way, we did this in collaboration with the security group, Professor Yan Chen at Northwestern. But this is an interesting direction. Also, like, to me, I'm not against, I actually like the idea that the developer express knowledge about the algorithm, not in an architecture specific way. Express knowledge about the algorithm, which might include request for security guarantees on a certain code or data. And then the compiler should lower down that concept to enforce some property at low costs. I like that type of approach. We didn't do that in that way, but I like that type of approach. Like the simplest example, and will be, this is a naive example, but is I have an array, and right now you only express this as an array. And maybe that is where you store the password. Well, you should say that, and that should be in the programming language concept. So now the compiler knows that this is an array that holds the password. So when you lower it down, you should lock that array into the cache, avoiding that to go through the memory controller, which somebody might attack your hardware and spoof the memory and the pass that attach the DRAM and the memory controller, and then get the password because you didn't access the password that often. You get called and you get swapped. But that's an example. It's a naive example. And of course, you cannot lock every array in the cache, right? The cache are not big enough. Great question. Great question.
Your question? You don't have any question? No, you don't have questions.
If you're watching my YouTube video about tutorials on Noel, good job.
Yes.
Let me know how things go.
I added to the YouTube live stream the links to Noel's GitHub page and
Thank you.
the main paper. So feel free to check
you.
it out, the audience later on.
Can you also add the link on my website on the software? So
Okay,
that is
sure,
where
yeah.
I keep all the links also on the tutorials.
Sounds great.
Thank you.
So if there is no further question, thanks a lot, Simone, again for the great talk. I'm extremely interested on just going to the computer now and just checking all of those tutorials.
Please do it. Please do it. Please do it. By the way, I just to show you how much I really like this Noel and the infrastructure. While I was so at 1:30 I was in. By the way, thank you for the space that I was able to use. At 1:30, so half an hour before the start, I actually fix a bug and push it on GitHub.
I saw 3
You saw
hours
it?
later.
It is an obsession. That's why my wife is a saint. It's crazy. Sometimes I wake up in the middle of the night because I come up with something and I
You have to implement.
Yeah.
That's good.
But
So
I don't know if it's good.
as long as it's not complaining. Yeah. Okay, so thanks so much again for the
Thank
great
you.
talk. Thanks, Simone, together, and everyone.
Thank you, guys. Thank you.
Thanks everyone for joining over YouTube. Stop the live stream. I don't have to.